This video is about chapter 22, about comparing two proportions. Now, what you'll see from here until the end of the year is that we will start looking at different types of confidence intervals and different types of hypothesis tests. And so here is another confidence interval and a hypothesis test that we can look at when we are comparing two proportions. By the end of this video, you should be able to know how to find the standard deviation for the difference between two proportions. You should also be able to find the confidence interval for the difference between two proportions, and there's 4 steps. Check your conditions, state what confidence interval you are going to find, calculate that interval, and then give a conclusion in context. You should also be able to explain what pooling is and when to use it. And finally, you should be able to perform a hypothesis test for the difference between two proportions. And a hypothesis test has 5 steps. You first state your hypothesis and alpha level. You check your conditions. You state what test you're going to do. You calculate the p-value, and then you give a conclusion in context. So first, let's talk about comparing two proportions. So far, we've only discussed testing to see if a single proportion is greater than, less than, or not equal to some hypothesized value. Okay? But it's more common to ask about two proportions if they are equal or not. Okay? For example, do men take more risks than women? We'll look at an example of that later on. Is the failure rate the same for freshmen and seniors? Do individuals over 65 have a greater chance of getting cancer than individuals under 65? Okay. Is the success rate of this medication better than the success rate of the current used medication? Okay. You're frequently asking about comparing two proportions. It's probably a more common question to ask than the one proportion case. Okay. Now, let me point out that the 1 proportion z-test and the 1 proportion z interval are not sufficient here because both proportions vary. So it changes the standard deviation or the standard error for these two, this confidence interval and the hypothesis test. So let's look at how to find the standard deviation when you are comparing two proportions. Okay. It comes back to the Pythagorean theorem of statistics, which, let me remind you, is the square root of the standard deviation of one squared plus the standard deviation of the other squared. Okay. Also keep in mind that x and y must be independent. Okay, that'll show up later as we check some conditions about two proportions. Okay, now we have been using the square root of pq over n formula, so we plug that in. If you square it, you will get simply pq over n. So it kind of ends up looking like this down here in the box. The standard deviation of p1 minus p2 is equal to the square root of p1 q1 over n1 from the first proportion plus p2 q2 over n2 from the second proportion. Okay, so a sampling distribution for two proportions. Okay, there are some assumptions and conditions. Some of these will look familiar to you. You'll see similar ones throughout the year. Okay, the independence assumption that within each group, the data is collected independent from the others. Okay, randomization, where each group should be drawn at random or generated by a randomized comparative experiment. Okay, the 10% condition says you should not exceed 10% of the population if you are drawing without replacement, which is how we usually draw samples. The independent group assumption is a new one. Okay, the two groups must be independent of each other. That's kind of where that standard deviation, the Pythagorean theorem of statistics comes in, where the two groups must be independent of each other. Okay, and finally, the success-failure condition, where both groups are big enough that at least 10 successes and 10 failures have been observed. Okay, now on the AP free response questions, I've noticed the two that they focus on the most, that they're looking for, are the randomization condition and the success-failure condition. Make sure you check both of those, and you have to plug numbers into these. Okay, these equations, you have to plug numbers in and check with numbers from the problem. You can't just say, well, there's at least 10 in both of them. You have to actually plug numbers in as you check the success failure condition. Okay, here is the purple box from the textbook about sampling distributions. And nothing is brand new here that we've not talked about already, but here's the formula again if it's not yet in your notes. Okay, here is a confidence interval for two proportions. Okay, the most important thing you're going to see is this equation right here. You will have to check conditions, the same ones that we saw for the sampling distribution. Okay, but the formula here is P1 hat minus P2 hat plus or minus Z star, the same Z star we used previously for proportions, times the standard error, but that standard error is a more complicated more complicated equation, so I kind of separate it, but you can write it down all together if you want. Okay, that's basically it. I want to give you an example of confidence intervals. Seatbelt use was recorded at 161 locations in Massachusetts using random sampling methods developed by the National Highway Traffic Safety Administration, NHTSA. Okay, that's important because if you ask people if they wear their seatbelts, they're always going to say yes. So you have to find some other way of sampling, and I guess this National Highway Traffic Safety Administration found a way to do this, do a random sampling method. So of the 4,208 male drivers with female passengers, 2,777, or 66%, were wearing seatbelts. But among 2,763 male drivers with only male passengers, 1,363, or 49.3%, wore seatbelts. Okay, how much difference is there in the proportion of male drivers who wear seatbelts when sitting next to male passengers, and the proportion who wear seatbelts when sitting next to a female passenger? Okay, so this is a pretty big difference, especially when you're dealing with a huge sample like we are here. Okay, and so we can look. The question is asking about the difference. How much is the difference? Okay, so it's asking for a confidence interval. Now, when you find a confidence interval, you must go through 4 steps. The first is checking conditions, and the two most important to check are the randomization condition and the success failure condition. I will check the randomization condition by simply stating that they are using random sampling methods. The data was collected using random sampling methods. Okay, and I will check the success failure condition. Just to organize my data, I will say with female passengers, there were, let's see here, 2,777, which had seatbelts, which is more than 10. It was actually with belts, which is more than 10. And there was 1,431 without belts, which is more than 10. And then with male passengers, there were 1,363 with belts, which is more than 10. And there was 1,400 without belts, which is more than 10. Okay, so I will now say the conditions are satisfied, and so I will perform a 2 proportion Z interval. Okay, I've checked my conditions and I've stated what test I'm going to do. I should next calculate that interval. There we go. Okay, so the formula altogether is I'll call it P sub F hat minus p sub m hat plus or minus z star square root of p sub hat f q sub hat f over n f plus p sub hat m q sub hat m over n, sorry, lowercase n sub m. Okay. Now, if your subscript notation is not super clear, you should state somewhere, what is what. But I think sub f and sub m is clear enough that this is with female passengers and male passengers that I think I'm okay. All right. So plugging some numbers in from the problem, there were 66% of male drivers with female passengers who were wearing seatbelts, and the male drivers with male passengers, only 49.3% were wearing seatbelts, okay? Plus or minus. The Z star value I will use, I'm going to do a 95% confidence interval, and so I'm going to use 1.96, okay? Square root of, now plugging some numbers in, I get 0.66, and the percent not wearing seatbelts with female passengers was 0.34, and the total number of drivers with female passengers was 4,208. Okay, and with male passengers, 493 were wearing seatbelts, and 0.507 were not wearing seatbelts out of 2,763 that had male passengers. Okay, so if you calculate that, it turns out it simplifies to be 0.167 plus or minus 0.024. Kind of make that a little clearer. Plus or minus. Okay, and so what we get is between 14.3% and 19.1%. So here is my conclusion. I am 95% confident that the difference in proportions, I'll say percent, of male drivers who wear a seatbelt with female passengers and just simplify it with male drivers with male passengers is between 14.3% and 19.1%. Okay, and that's the whole process. Okay, so I first checked my conditions, I stated which test I'm doing, I actually found the confidence interval, and then I stated my conclusion in context. Okay, now I'm sure you're wondering, isn't there a fast way to do this on your calculator? Okay, and the answer is this part, yes. Okay, actually calculating that confidence interval, there's a faster way. We'll cover that more during class, just because if I explained it in the video, it wouldn't really help you very much. But there is a 2-prop z-int function on your calculator that we will look at using during class. The next topic is hypothesis tests for two proportions. Now, before we get into actually doing a hypothesis test, there's a couple of ideas that I need to explain first. And the first is pooling the data, what it means to pool your data. When we perform a hypothesis test, we will almost always have our null hypothesis to be that the two proportions are equal. Okay? And we could use a standard deviation equation like the one we used just a minute ago for the sampling distribution, but we will, our null hypothesis will be that the two proportions are the same, okay? And so what we need to do is pool the data together, means combine them together as we do our calculations. We're doing it based on the assumption that the two proportions are equal. Okay, and when you pool the data, you're finding the total number of successes in both groups divided by the total number of people in both groups, and that gives you a kind of average, average p hat value. Okay, and then we can plug it in using a similar formula to the one we used before, but now we're using the pooled p hat and q hat for both of them, divided by, you know, the sample size for each sample, but we're using the pooled p hat and q hat value in all of our calculations. Okay, and that also includes the success failure condition, that we'll use the pooled value as we're checking our success failure condition. So here is the purple box from the textbook. It outlines that our null hypothesis will usually be written this way. P1 minus P2 equals 0. Now there's nothing wrong with saying P1 is equal to P2. That's what it's mathematically equivalent to. But for the calculation, you'll see that having it be 0 helps out kind of with your calculation in knowing that a 0 should go right there in the equation. Okay, and then we're using a pooled value, which is the total number of successes over the total number of people, or I guess sample size. And here's the standard error, and then here is the test statistic. It should look very much like x minus mu over sigma, where mu is 0, because that's what it's hypothesized to be. X is this value, the difference that you saw in the samples, divided by the standard error from the pooled values. Okay? So here is an example of a hypothesis test. The National Sleep Foundation asked a random sample of 1,010 US adults questions about their sleep habits. One of the questions asked about snoring. Of the 995 respondents, 37% of adults reported that they snored at least a few nights a week during the past year. Would you expect that percentage to be the same for all age groups? Okay, if you split it into two age categories, 26% of the 184 people under the age of 30 snored, compared to 39% of the 811 in the older group. Okay, so the question we're asking is, are the snoring rates for the two age groups really different? Okay, because the difference here seems, like a pretty big difference, and so we're wondering, is that just based on chance, or can we conclude that older people are more likely to snore? Now, a hypothesis test has 5 parts. You will first state the hypotheses and alpha level, check the conditions, state what test you're going to perform, find the p-value, and then give a conclusion in context. So let's start. The null hypothesis will be that p sub old minus p sub young equals 0. There's no difference between the two proportions. Okay, and the alternative, p sub old minus p sub young. Okay, now this is an interesting one because of the data we're kind of asking, oh, is it more likely that old people snore? But we're supposed to make this hypothesis before we collect any data, and so let's just ask to see if it's different. Okay, instead of it being greater than 0, meaning old people are more likely to snore, let's just have it be not equal to 0, seeing if there's a difference between old and young people and how likely it is that they're going to snore. Okay, and I'll state my alpha level to be 0.05 because I have no reason for it to be higher or lower than normal. Okay, hypothesis, check. The next thing we'll do is check conditions. The two most important ones are the randomization condition and the success failure condition. And so it was a random sample, and so I'll just say that the data was collected using a random sample. Okay, now I can check the success failure condition using a pooled value. So here's how you find your p hat pooled. Hat means it comes from my sample. There were, let's see here. I need to find out how many people. So the 26 times 184 turns out to be about 48 people. I'm rounding. So I have a whole number of people. And the 38% of 811 turns out to be about 316. Okay, so the total number of people that snored, let's see, our old was 316 plus 48 over a total of 811 plus 184, which ends up being about 0.3658. Okay, that's my p hat pooled value. So yeah, that's good enough. Let's go down here and let's look at n old times p hat pooled. Now there were 811 people that were over the age of 30 times the pooled value 0.3658, which is about 296.7, which is bigger than 10. And the n sub old times q hat pooled, which is 811 times 0.6342, which is about 514.3, which is bigger than 10. And n sub young times p hat pooled equals 184 times 0.3658, which is about 67.3, which is bigger than 0. And n, the number of young people, times, q hat. Q hat pooled is 184 times 0.6342, which is about 116.7, which is bigger than 10. Okay, the conditions are satisfied. So I will perform a 2 proportion z test. Okay, so I have stated my hypotheses, I checked my conditions, I've stated what test I'm going to do, and now I actually need to calculate the p-value. Okay, I will first start off with finding the standard error. The standard error equation is the square root of p pooled q pooled over n old plus p pooled times q pooled over n young. Okay, which when you plug the numbers in, you get 0.3658 over 811. Oops, I forgot q. 0.6342. There we go. Plus 0.3658 times 0.6392 over 184, which ends up being about 0.03933 is our standard error for the difference between these two proportions. Okay, let me remind you, so here's our normal curve. The hypothesized difference is 0, and the standard error is 0.03933. So, and I want to look at the difference. Now, the difference from these two values, the difference here was 13%. Okay, so that's the observed difference. Okay, so the difference is 13%. Okay, so I'm going to do norm CDF, and it's going to be 0.13, comma 9999 infinity. The hypothesized difference is 0, and the standard error is 0.03933. Okay, now I grab my calculator and do norm CDF, 0.13, comma infinity, comma 0, comma 0.03933. and I get a value of 0.0004743. Okay, now let me kind of remind you really quickly, because this is important, that my alternative hypothesis was not equal to 0, which means it's a two-sided test. I must take this p-value and multiply by 2 because I have two sides that I need to deal with. Times 2, and I get 0.0009486. Okay? And that is my p-value. So the next thing that we do is we state the conclusion in context, and it goes like this. With a p-value of 0.0009486, which is less than alpha, which is equal to 0.05. Now, because it's below alpha, I will reject the null hypothesis. Okay, and say there's enough evidence to conclude that, and my alternative hypothesis was that there's a difference between the proportion of men over and under 30 that snore. That there is a difference between the proportion of men over 30 and under 30 who snore. Okay, and that is the hypothesis test. I first stated my hypothesis and alpha level. I checked my conditions. I stated what test I'm going to do. I found my p-value, and then I gave a conclusion in context. Okay, now again, like a confidence interval, this part, okay, can be done on a calculator to find the actual p-value, but we'll do that in class when you have a calculator in front of you. But there is a 2-prop z test function on your calculator that you can use. Okay, this video was about comparing two proportions. You should now be much more familiar with finding confidence intervals and performing hypothesis tests for the difference between two proportions. Thank you so much for watching.